laptop is in the process of slowly dying, so I would expect PowerPoint to crash at least once during lecture, so please be understanding. We start PowerPoint as soon as that happens. Today we'll be talking about hidden Markov models. I alluded to this in the previous lecture. It's a generative probabilistic model, and it's designed for things like sequence modeling, where you get a sequence of predictions rather than just make a sequence prediction at a time. So what is an example of sequence prediction? Probably the most canonical one in the machine learning community is part of speech tagging. The basic idea is that the X is a sequence of words, like fish sleep, the dog ate my homework, fox jumped over the fence. And the Y is a sequence of part of speech tags, such as noun, verb for fish sleep. The dog ate my homework. It corresponds to determinate noun, verb, determinate noun. The fox jumped over the fence, determinate noun, verb, composition, determinate noun. So this is sequence prediction. So the sort of standard prediction problem would be train a model such that given any X, I can predict the correct Y, where the X and Y are both sequences, instead of just where the Y is not just a single prediction. So there's a few challenges in sequence modeling and sequence prediction. Obviously, it's a multivariable output, unlike every types of prediction problem we've talked about so far. It's not really simple classification like binary classification or regression. You have to make multiple predictions simultaneously. Furthermore, the length of the output is not fixed, right? It's a variable length input-output. The length of your output sequence depends on the length of your input sequence. So you need a model that can somehow scale its output to the length of the input. So let's talk about multivariate outputs in sort of from a simple perspective, which is multiclass prediction. Multiclass prediction basically posits that there's a number of different classes you can predict, not just binary. And the simplest thing you can do in multiclass prediction is to keep a set of models. In the linear case, it's a set of linear models for every class, right? Then you score every class according to the model parameter in every class. And then you pick the class that has the highest score. So this is what you would do for simple, basic multiclass prediction. And this is what you would use in multiclass prediction for simple, relatively simple multiclass prediction problems like, is this an animal, person, or vegetable? Three-class prediction where capital K equals 3. You can imagine doing this for every part of speech tag, for every word. There would be sort of capital K equals 6 in this simple example. But in general, you might want to do this for an entire sequence of tags at a time. So in that case, the number of tags, classes, is equal to the number of possible sequences of tags. Right? So multiclass prediction, if you were to apply directly, you would try to train a model that can predict all possible length M sequences as a different class, where M is the length of the input. So for example, for M equals 2 and 6 different tags in each sequence, these are a sampling of the different classes that you can predict. Now if you think about this and think about what would happen if the number of the input sequence and the output sequence was greater than 2, like 3, 4, or 5, or in general length M, there's L to the M different classes, right? You need to score L to the M different possible predictions for a length M input instance. So just for length 2, that's 36. So I just showed you a sample of 36. For length 4, 5, 6, it just grows exponentially fast. Right? So the conventional multi-class view, as applied to sequence prediction, variable length sequence prediction, does not work and doesn't scale. There's an exponential explosion in the number of classes, so this is not a tractable approach to sequence prediction. Just another example. Treats every combination as a completely different. The reason why naive multiclass is intractable is because it treats every different combination of tags as completely different. It has a completely different scoring rule for every different combination of classes. Like, has a scoring rule for determiner, has a scoring rule for determinate noun, when clearly, at least at an intuitive level, these two classes are somehow related to each other, but we're not modeling that at all. We're just modeling them completely in a completely unstructured way. And that's what leads to the exponentially large representation requirements. Okay, so this is bad. We don't have the capacity to be able to model something like this in an unstructured way. Let's take the other extreme, completely independent classification. We're making a super strong structural assumption that we should treat every word completely independently, right? So what does that mean? That means we simply look at we take a sequence of words, X, and we simply look at one word in that sequence independently at a time, and then predict a label Y, a part of speech tag for each word independently. Right, so we predict for X, for I independently, for fish independently, for often independently. And then we concatenate the predictions to form our sequence of predictions. So this is the other extreme. So now the number of classes equals the number of part of speech tags, so 6 in this example. That we're doing 6-class classification. We're doing it multiple times, m times if it's a length m input, and then we just simply concatenate. So this you can certainly solve using standard multiclass prediction, right? You just learn a model, you just learn a single model that for every word, it predicts the probability of that word corresponding to a part of speech tag, and then this model can be applied to every token in this sequence. Now, fish, of course, is an ambiguous word. It can be both a verb and a noun. And what that means in the independent case is that, well, let's say in our data set, fish occurs as a verb 75%, a noun, 75% of the time, and as a verb 25% of the time. If I make an independent prediction for every sequence, for every token in the sequence, the prediction will be noun, adverb, excuse me. When the correct sequence is noun, verb, adverb. So why do we make this mistake? Any guesses?
Don't consider the context.
Lots of people said something. That's right. We assumed that these are independent when actually they are not. Right. We took the other extreme just made because we sort of failed so spectacularly to try to model everything simultaneously. The model complexity blew up in our face. We took the other extreme, model everything completely independently, and now we're making predictions that are not right. So another way to phrase this is that we're ignoring the context between words. That's a terminology people in the community often use. We're ignoring the context between words. Right. Independent predictions, we ignore word pairs, for example. Right. Fish in isolation, in absent other information, fish is more likely to be a noun. But conditioned on following a noun or a pronoun, fish is more likely to be a verb. Right? You don't often see noun or pronoun noun as a part of speech tag sequence in the English language or any other language. So if you just look at pairs of words, this is called a first order dependence. Right? Second order dependence in this terminology considers all triplets of words. And then third order considers all quadruplets and so on and so on. Arbitrary order gives you back to exponential size. Right? So this is how we control for the complexity of our model class while modeling some amount of structured information is through sort of this type of concept. Zeroth order is the independent multiclass. Arbitrary order is the naive multiclass with exponential size, and then there's a sliding scale in between. And in this lecture, we'll primarily look at first order Markov models or sequence models. In general, we can sort of internalize the concept so you can generalize to higher order sequence models in a straightforward way. So this is the definition of a first order hidden Markov model. And by the way, Markov, a model is considered Markovian if it makes this type of independence assumptions, where the dependence is only local to a small window. That's why it's called a Markov model. And I'll explain why it's a hidden Markov model closer to the end of this lecture. So abstractly, you get a sequence of tokens X in the input token space, which is a sequence of words. You get another sequence Y in some output token space, a sequence of part of piece tags. And then the first order hidden Markov model is summarized by these four model components. We have a local probability distribution that's its condition on the ith token, conditioned on the current token that we're looking at being y sub I, what is the probability that y sub I generates x sub I? So this is your standard naive Bayes component. Okay, this is basically the same as your naive Bayes from the previous lecture. This is a transition probability that says, conditioned on the current state being y sub I, whatever y sub I is, what is the probability distribution of the next state, or the next part of speech tag? There's a special case of this, which is what is the first part of speech tag, probability of the first part of speech tag conditioned on the start state. So y of 0 is a special token that never changes. It's just the sort of a virtual start state. So this basically models the probability of any part of speech tag starting a sentence. Right? And then there's an end, and this is not always used, but there's also an end transition. So what is the probability of this part of speech tag being the end of a sentence? So more precisely, given that we're at this part of speech tag, what is the probability that it'll end the sentence rather than transition to another part of speech tag? So here's the graphical model representation. We have a special start state, end state, and then we have these conditional dependencies that are sort of modeled. And so all the probability, the joint probability of this Hidden Markov model and this graphical model representations is equivalent to this independence assumption that we only need to model these components and then just multiply them together. Right. So the probability distribution of this part of speech tag variable, the distribution of this guy only depends if you condition on whatever this guy is and whatever this guy is. Sorry, condition on whatever this guy. Excuse me. Condition on whatever this guy is. It's independent of everything else, expressed here. And then if you condition on this guy, the probability distribution of this word is independent of everything else. Any questions? Yeah.
What if the word which is like more than one part, which would, for example, I like machine learning, and machine would imply learning being a verb, but I like it's like it actually becomes like a whole.
Right. So machine learning would be something that a simple HMM hidden Markov model would not be able to model correctly model.
So you would need like multiple.
Because machine learning is actually a two-word single entity. Right,
Okay,
it's actually a multi-word single entity, right? So that is something that this model would not be able to. This model assumes that every word is its own entity, if you will, right?
But you would simply have to like extend.
There are extensions. There are. If you really want to use a Markov model, like a first-order Markov model, you can run a pre-processing step that recognizes all multi-word named entities, collapses that into a single token. So you have in your vocabulary, you would have machine learning as separate things, and then machine learning as a separate single vocabulary entity, right? It will collapse that into a single token. So there are pre-processing steps you can do. They're called named entity recognizers that can understand that there's a sequence of words that corresponds to just a single noun. Right? But if you don't, and there are other things you can do. I'm just suggesting one if you really want to still use a first-order hidden Markov model. Is there another question?
Can this also be used in generating meaningful sentences?
Yes, this is a meaningful, syntactically correct, perhaps not meaningful. Meaningful. So this is a generative model, as I'll show, as described here, right? So if you fit this model to data, you can given these independence assumptions, you can generate new sentences according to this distribution. This distribution captures syntactic transitions, right? It does not capture semantic transitions, necessarily. Right. Does that make sense? Yeah. And this is, of course, an area of an intense research in the natural language processing computational linguistics community. And what I'm presenting here is simply something that, the simplest thing you could do. Okay, so just a reminder, this is just the probability, joint probability as as defined by this graphical model structure, and these are the definitions. Okay, so one of the nice things about this model is that if you look at the conditional distribution of the x sequence given the y sequence, it actually factorizes completely independently. Right? If you condition on this, if you fix the sequence of y, the x's are completely independent of each other. Right? So given a part of speech tag sequence y, I can compute the distribution of every word in the sequence completely independently, which means I can sample independently. And so you can see here why this doesn't preserve semantic meaning across the sentence. It preserves syntactic meaning, but not syntactic transitions, but not semantic meaning. And this is, of course, a modeling assumption. It's a simplification of the real world. So what is the complexity of a hidden Markov model? Well, it's basically the complexity of storing, it's basically the number of parameters in these probability functions that define these probability functions, right? This one is all possible word tag pairs, part of speech tag pairs. So if you have 1,000 words in your vocabulary and 6 part of speech tags, this probability table has 6,000 parameters. This is basically all state-state transitions, so it's essentially quadratic in the number of tags, part of speech tags. So this, and then this is, these two are sort of negligible. They're just linear in the number of part of speech tags. So the complexity of this model is basically linear, assuming that is basically linear in the number of part of speech tags times the number of words. Right? Because this in practice, the number of parameters in this probability function, or probability table really, dominates the other number of other parameters. And this is actually why people often use the hidden Markov model assumption, because we can also, think about reversing the independence, right? Given the x, the y's are independent, but then we'll have to model the probability of x given x, which is quadratic in the number of words in your vocabulary. And that's a much bigger number. Okay, so what is the relation to naive Bayes? Well, in naive Bayes, if you just simply remove the dependency from token to token, what you get is a naive Bayes sequence of disjoint naive Bayes models. So in some sense, you can think of this as the sequential version of a naive Bayes model. Okay, so let's just look at a very simple, concrete example. We have let's say there's two words in that vocabulary, so either fish or sleep, and our part of speech tags only has 2 tokens, noun and verb. And so here's the conditional probability table. We're given the y's, what is the x, right? So this is the naive Bayes subcomponent part of the hidden Markov model. So condition on y being the current part of speech token being a noun, it has 80% probability of generating a fish and a 20% probability of generating the word sleep. Condition on the token being a verb, it has a 50% probability of generating a fish and 50% probability of generating sleep. So from this, because it factorizes given the y's, you can compute the probability of a tag sequence given the tag sequence y, you can compute the probability of fish sleep given some tag sequence like noun verb as the independent products. Okay, so hidden Markov models are also generative probabilistic models. So they model the joint distribution of p of x comma y. So we can generate samples from this distribution if we want. Right? If this is our model, if this is our simplified model of the test distribution, we can draw samples that preserves the statistics that we're modeling, which is transition probabilities from tag to tag and generating probabilities from tag to words. Right? So first consider the conditional distribution. Suppose we've already sampled the y. Suppose we first sample the y, then we want to sample the x conditioned on the y. Well, it's trivial, right? It factorizes independently. Right? So given a tag sequence y that we've already sampled, we can sample each word independently. So this is a trivial sampling process. Right? So each of these is basically sampled according to the same way you'd sample from a naive Bayes model. So that gives us some insight about how we might do sampling in a very easy and straightforward way, despite this being a sort of, a priori seemingly complex distribution to sample from. So the way that you would do sampling is called forward sampling. Here's how it works. So here's another way you could represent a hidden Markov model, right? In terms of the state transitions. So from the start state, you have an 80% probability of, from y0, the start state, you have an 80% probability of transitioning to noun, and then 20% probability of transitioning to verb. If you're currently in the noun state, you have an 80% probability of transitioning to verb, 20% probability of transitioning to noun, 80%, 10% to n, and 10% back to noun. Let's just say for this model. And then all of them have some probability of transitioning to n. So here's how forward sampling works. Actually quite simple. You initialize the current part of speech tag as the special start state, and you're currently at the 0th word, so the beginning, the start state. You increment your word, your token counter in your sequence. You sample your next part of speech tag according to this distribution, right, which is represented here. So if you're currently at the start state, you have a 20% chance of sampling word, verb, and an 80% chance of sampling noun. If this state is n, if you sample the n state, then you quit. Otherwise, given the sample, you sample an x from p of x given y, which is one of these columns. And then you go back to step 1, increment your word counter, your token counter in the sequence, and repeat this process until you've sampled the n state. And this defines a legitimate sampling process that generates samples from this distribution. People often ask about, what if I just want to sample p of y given x given a fixed length, and sometimes people choose to do this without modeling the end state. It's not very common, but some people choose to do this. Okay, so another property of hidden Markov models is that they're often called a memoryless model. This is also what a memoryless model basically means, that if you know what the current state, the current part of speech tag is, I often refer to that as state. If you know what the current part of speech tag is, if you condition on it, you don't need to condition on anything else before it, right? If you want to model the probability distribution of the remaining words and the remaining part of speech tags, given the first k words as part of speech tags, it actually is completely independent of anything but the current part of speech tag. And this is called a memoryless model. We don't need to remember anything before the current part of speech tag if we condition it. And this is basically another way of saying this is why this model is compact in its representation. Right. The memory bottleneck is here. And so if you have a simple state representation, which is like saying my state directly corresponds to a part of speech tag, there's no way you can capture semantics. You can have a much more complicated state representation. You can model part of speech tags, some notion of emotion, sentiment. You can model more than just part of speech tags in your Ys. But now the state space becomes much more complicated. Okay, so this is the hidden Markov model. I'm now next going to talk about how how to do complex prediction and learning from it. Are there any questions about the structure of the model? Okay, so the Viterbi algorithm. So the most common prediction problem, given a trained hidden Markov model, I'll talk about training a hidden Markov model at the end of the lecture, but right now let's assume the hidden Markov model has already been trained. We want to make predictions from it. The most common one, of course, is given an input sequence of words, predict the sequence of part of speech tag, in particular, predict the most common, predict the part of speech tag sequence that has the highest probability. According to our model. So the naive approach is, of course, let's just try all possible y's, and then choose the one with the highest probability. This is correct in the sense that it'll give you the right answer. Can anyone see what's wrong with this approach? Why you might not want to do this in practice? Yep.
It might go down a lot fast.
Yes, and do you know how many? Order of magnitude?
I guess like the number of y's that you have.
This, yeah, which is a sequence of length equal to the length of this.
To the power of the number of particles speaking.
That's right. So it's exponential. It's essentially exponential, right? The number of y sequences is the length, the number of part of speech tags raised to the length of the sequence that you input. It's a lot. It's quite a big number. So you don't actually want to do naive exhaustive search. Just a reminder about the Bayes rule. If you want to solve for the y that maximizes this probability, it's equivalent just via Bayes rule to finding the y that maximizes x given y times p of y. Right? And this, if you look at the Markov model, independence assumptions is a lot easier to think about, right? We know that the p of y factorizes into this, and we know that the p of x given y is completely independent of each other. It completely factorizes in an independent way. So here is the sort of the key observation that motivates the Viterbi algorithm, which is a dynamic programming algorithm. If you are familiar with dynamic programming, this is sort of fairly straightforward. So here's and the notation is a little heavy, but you can sort of look through it at your leisure. At the class, there's also a recitation tonight reviewing the Viterbi algorithm and one other algorithm that's used to do inference and predictions in hidden Markov models. So, okay. So from this slide, we know that making the max prediction is equal to this, right? So here I just did something very simple. Instead of doing an argmax over the entire sequence, I equivalently rewrote this argmax as taking the maximum over the last token and then a maximum over the first n-1 tokens. Right? So these two statements are completely equivalent, but I just rewrote this for mathematical convenience because it helps motivate the intuition. Okay. So now I'm going to expand out this compact mathematical notation to sort of explicitly, uniquely identify the last token and the rest, right? So here, I can equivalently write this as the probability of the first n-1 tokens and the first n-1 words times the last token. This is just the mathematical equivalence from the identity, from the definition of hidden Markov. Right. So basically, this is a memoryless property, right? If we've already solved this problem, the problem for the first n-1 for the subsequence, we can easily solve. So if we've already solved this problem, we can easily solve the problem of finding the next most likely sequence, by just enumerating over just a few things. Right, this is a recursive definition, right? I could define this for any subsequence xy of the full sequence, and this recursive definition holds. Like if I look at this probability, right? it again expands recursively. You can recursively expand this in this way. So here's the dynamic programming approach, which is, so Viterbi is the specific instance of dynamic programming for hidden Markov models. Dynamic programming is just a more general name for these types of algorithms. These algorithms basically exploit some type of memoryless property in order to not have to explicitly enumerate all the possible solutions. So we're given an input sequence X. And let's say we're in the middle of the sequence. We're in the middle of computing the optimal solution, and let's just assume that we've computed the best length k, where k is some number in between 1 and m, prefix ending in each tag. Right. So what does that mean? That means y of k of v is the best sequence of length k that ends with the part of speech tag v, which is verb. And y of k of noun is the best part of speech tag of length k that ends in noun. Right. Let's assume that we've already solved. We already know these. Right, for up to iteration k. The claim in dynamic programming, the dynamic programming claim, and it manifests itself in different contexts for different problems, differently for different problems, but for the Viterbi version of dynamic programming for hidden Markov models, the claim is that now I've already computed the best possible sequence of length k ending in verb, ending in noun, and so on and so forth, it's easy to compute the best possible sequence of length k plus 1, ending in verb and noun, and so on and so forth. All you have to do is iterate over all the previous solutions that you've already computed for up to length k, concatenate that with verb, look at the probability, and pick the one that's the best. That's all you need to do. And I'll give you an operational example in the next couple of slides. And if this is easy, then I've satisfied the assumption that I've already, if this is easy, then I can recursively say that after I do this computation, I've satisfied this assumption for k plus 1. And then it's easy to do this for k plus 2, and so on and so forth. Therefore, it's easy to do this for the entire length of the sequence. Right, it's an inductive proof. Yeah?
Can you explain again the notation?
Yeah, sorry, the notation is a little heavy. So this is just the first the first k minus 1 tokens, the part of speech tags. This is the first k words in your input sequence. I'm concatenating the first these k minus 1 input sequences part of speech tags with the token verb, and I'm computing that